Hello and welcome to LFI Educates. Today in our physics class of grade 12, we are going to start this chapter number 4. That is moving charges and magnetism. Here the word moving charges, that you already know, moving charges means electric current. Current is defined as the rate of flow of charge. And the second part, that is our magnetism. In this chapter, you will study the correlation between electric current and magnetism. So, before we start the chapter, first of all, let us know what is magnetic field. Magnetic field is a region or the space around which the magnetic effect can be felt. If you keep one magnet, then there will be a field region around the magnet where its effect can be felt. That region, this is not the exact field of a magnet, but I am just giving you the idea that there will be a boundary or a certain region around which the magnetic effect can be felt. That region we call it as magnetic field. This region we call it as magnetic field. Or it can be even a current carrying conductor. Suppose this is a conductor carrying current I. It will also have its own field. We are going to study about that field. How the structures will look, we will come to know later. First, to know the definition, the region, here also you get region around the current carrying conductor where its magnetic effect can be felt. That region we call it as magnetic field. It can be a magnet or it can be a conductor carrying current passing through a conductor. The SI unit of magnetic field, we call it as Tesla. The SI unit of magnetic field is Tesla. We write it as T. It's the name of a person who made the Tesla coil. Now this Tesla, it can be written as Weber per meter square, or it can be Newton per ampere per meter. So this Newton per ampere per meter or Weber per meter square, we call it as Tesla. That is our SI unit of magnetic field. In CGS system, the unit of magnetic field is Gauss, that you have come across earlier. Gauss theorem or Gauss law in static electricity, you have come across, is a person's name, Gauss. In CGS system we measure in terms of Gauss. Now, for quite long, scientists were believing that these two entities, electricity and magnetism, are completely different from each other. They don't have any relation. Until the year 1820, Hans Christian Ostrich came across with his experiment. In his experiment, he proved that any wire or any conductor, whenever current is flowing through that conductor, it develops a magnetic field. That was his experiment, and that led to the discovery of electromagnets, and from there on the study started between the two relations between electric current and magnetism. So let us see his experiment first, the Ostrich experiment. He took a straight conductor, suppose this is a straight conductor AB. He kept in the north and south direction. This is your north, south, this is east, this is west. He kept the conductor in the north-south direction. Then he took one compass needle over it. The compass needle, as we know, always it points in the north and south direction. He kept like this. Then he took some conducting wires and then one cell or a battery along with one switch. When he allowed the current to flow through this conductor AB, if I switch it on, we know that the current will start to flow from the positive terminal, from higher potential to lower potential. When current started flowing, then this compass needle showed some deflection. It showed deflection this way. It started deflecting towards the left. And what he did, he tried to reverse the direction of current. Earlier, this part is positive and this terminal is negative. He changed the terminal. He allowed the current to flow in the reverse direction. This one became positive and now this is negative. Now in this case, current will flow in this direction from top to bottom. In this case, what he found out was the reverse effect. The compass needle started deflecting towards the right. It started deflecting this side. And then when he stopped the flow of current by switching it off, that is to open the circuit, by opening the circuit, when the current flow was stopped, it was observed that the compass needle comes back to its own original position, north and south direction. This was his experiment, and then with this experiment he concluded that whenever current passes through the conductor, then the conductor behaves like a magnet, or in other words we can say that it develops a magnetic field near the wire. Now this deflection in the compass needle which I have shown, when wire comes from the bottom part, it deflects towards the left. When current comes from the top part, the deflection is towards the right. You can keep in mind with the help of this rule called Snow rule. Snow rule says like this: whenever you allow the current to pass from south to north, downside is south, you can see here, and the top part is north, from south to north. If you allow the current to flow from south to north over the wire, then the deflection must be towards the west. The deflection must be towards the west. Again I repeat it once more. When current flows from south to north over the wire, then the deflection in the compass needle is towards the west. This is known as Snow rule. West is which side? You can see it is towards the left. So the deflection will be towards the left like this. And vice versa. If the current comes from north to south, if it comes from north to south over the wire, then the deflection will be towards the opposite of west. Is what you can see here very clearly. It is east. The deflection will be towards the east. This is the experiment done by Ostrich, and he proved that a current carrying conductor possesses magnetic field. Now, the next thing that you learn here in this chapter is about your Biot-Savart's law. Now, in this case, when current passes through a conductor and magnetic field is developed, what type of field is developed that you want to know, you can practically do it like this. Take one hard sheet of paper, the cover of your notebook. make one small hole in it. After making one hole, paste it with white sheet of paper on top of it, and take your straight conductor, allow it to pass through this hole and to come out this way. Then at these two ends, A and B, connect the conducting wires. One switch, you can take it. When you switch it on or close the path, then current will start to flow, and you can see here very clearly it is flowing from bottom to top, from positive terminal, from higher potential to lower potential it will flow. Take your compass needle, place it near the wire, then it will show you some direction. In the compass needle you have a pivoted magnet in the shape of an arrowhead like this. So top of the arrowhead you put one dot, bottom of the arrowhead also you put one dot, and then lift up the compass needle. Then again you place the compass needle, which side was the front part or the pointed part of the arrowhead, that side you have to keep the compass needle. There also the compass needle will guide you. This end you put one dot, lift up the compass needle. Then again place the compass needle here, see which side the arrowhead is, place the dot there. Like that, if you go on placing the dots, then you will find that these dots will form a circular pattern will form, and if you join all the dots, you can see the magnetic field line around the wire. Now, if you place the compass a little bit away from it, then you will get another similar pattern. They will form concentric circles. Around the wire, you will get concentric circles. Concentric circles are those circles which have the same center but different radius. Here you can see this radius is less, this radius is more. So like this, concentric circles will be formed. And to know the direction of this magnetic field, because magnetic field is a vector quantity, it must show specific direction. To know the direction, we use Maxwell's right hand grip rule. If you hold the current carrying conductor with the help of your right hand like this, suppose this marker is the conductor, I am holding it with the help of right hand. If the thumb points towards the direction of current, then the tips of the finger encircling the conductor will show the magnetic field lines. Now here the tips of the finger coming like this, like this, then you can see in your clock it is anti-clockwise. It will be anti-clockwise. So if the current comes from bottom to top, the direction of the field lines that you have drawn here, it will be anti-clockwise. It will look like this, anti-clockwise. The reverse is also true. If you allow the current to flow in the other direction by changing the polarity here, then the direction of magnetic field line will be clockwise. It will become clockwise, and that is given by right hand thumb rule, we say. And that is given by Maxwell. Now, if a straight conductor carrying current produces magnetic field line, then the strength of the magnetic field line near the wire will be more, we know. If it is away from it, it will become lesser and lesser. So to find out that one, the strength of the magnetic field near the wire, Biot and Savart together gave a law, we call it as Biot-Savart's law. Let us see this law. Biot-Savart's law. It is an experimental law. It does not have statement. Mathematical formula wise, we will write down the law. let me draw one diagram to understand this Biot-Savart's law. We'll take the wire in a curved way, like this. We'll take it. This is your wire. A small portion of the wire, we'll take it from here. This is a small portion of the wire. We call it as an elemental length of the wire. DL will write. Small. Whole length will be L. So small length taking, so I am writing DL. Now, if you allow the current I to pass through it, suppose current I is passing through this wire, then IDL will be called as the current element. Now, current has direction here. You can see it's going up. So, the direction in a curved path, we know that it will be tangential to the curve. So, I'll take like this, then tangent and drawing. This will be your IDL. Together we will treat it as vector quantity. Current with direction you are taking this time. Now, near this DL, anywhere, suppose I want to find a magnetic field here, dB, small current element, so we'll take magnetic field also small. B is a symbol we use for magnetic field induction. dB means very small magnetic field induction produced by this small current element IDL. Now let this position vector from DL, if you mark it as R, then the angle between IDL and R, let us take it as theta. Then the magnetic field induction at this point P, according to Biot and Savart, we can write like this. Magnetic field induction, it states that dB is directly proportional to the amount of current it flows. It is directly proportional, that means the strength of magnetic field will be more if the amount of current flowing through the wire will be more. If the elemental length that you have chosen is more, then also the field strength will be more at point P. It's directly proportional to sine of the angle between this IDL and R. IDL and R, this angle theta, sine theta, and it is inversely proportional to the square of their distance. Position vector we are taking it as R, distance from this point DL to P. So these four combined together gives us the experimental law of Biot and Savart. From equation 1, 2, 3 and 4, we can write dB is equal to, first we will write proportional to IDL sin theta divided by R square. Downside is R square. This law we call it as Biot-Savart's law. Now to remove the proportional sign here in magnetism, use a magnetic constant. We use a magnetic constant. dB is equal to mu naught divided by 4 pi ideal sin theta divided by R square, where mu naught divided by 4 pi has the value 10 to the power minus 7 Tesla meter per ampere, and this term mu naught is called the magnetic permeability, like your electrical permittivity was there, epsilon naught, and this law is given in a vacuum. Whenever we write naught here, we should know that the law is presented in vacuum. Now, this magnetic permeability is the capability of producing magnetic field lines by a magnet or a current carrying conductor in vacuum where no other substances are nearby. That we call it as permeability. Now, with this law, you can find out the magnetic field near a straight conductor, curved conductor, circular conductor. Everywhere we can find out using this formula. This one will take it as a formula. This Bhatt-Savart's law, if you write in vector form, if you write, then dB will write with an arrowhead vector quantity. This is mu naught divided by 4 pi. Then here IDL is a vector quantity. Then cross product will come here because sin theta is there. A cross B is putting here cross, and the two vector quantities are IDL and R. So IDL cross R divided by it will become R cube. Divided by R cube it will become. This is in vector form. If you break up this one, we'll get the same thing. Let us see. This is mu naught divided by 4 pi. IDL A cross B. A B sin theta. A B sin theta divided by, this is R cube. So if you cancel this one R, then you get here R square. It will remain the same. Mu naught by 4 pi. Ideal sin theta divided by R square. So this is the way to represent in vector form. Now, as you all know that two vector quantities, when we are doing the cross product, then what do you get? The resultant also must remain a vector. The resultant also must remain a vector. It must show direction. This dB must show direction. And how do they show? In class 11 you studied about vectors. If two vectors making an angle theta, then the resultant must be perpendicular to both of them. The resultant must be perpendicular to both of them. It will depend upon whether it is A cross B or B cross A. If A cross B is pointing up, then B cross A, if you come this side, then it will be pointing down. So here also, but it must be perpendicular to both of them. It must be perpendicular to ideal as well as it must be perpendicular to position vector here R. So in this case also it will be perpendicular like this. It will be perpendicular, but which direction? That you have to know. You can use the direction to find. You can use the clock rule, or we call it as the screw rule. Corkscrew rule also we say, like a bottle cap. If you rotate it in the clockwise direction, then what happens to the bottle cap? It goes down. It goes perpendicularly down. If you rotate it anti-clockwise, then the bottle cap comes up, and it comes out of the bottle. So here also the same rule is applied. You look here. IDL cross R, this arrowhead you can see, IDL cross R, is it clockwise or anti-clockwise? You can read nicely, it is clockwise. You can see very clearly it is clockwise. If it is clockwise, like your bottle cap clockwise, then it goes down. So this direction of dB will be perpendicular to the board. In your notebook it will be perpendicular to the paper inwards. Inside it is going. Direction of dB is inwards. So here you can write down the direction of dB is perpendicular to the paper inwards. Inside is going inside the board. In your notebook, it will go inside the paper, perpendicular to the paper, and dB must be perpendicular to both ideal and R. This also to be noted. dB must be perpendicular to both ideal as well as R. For both ideal and R, dB must be perpendicular. It must make an angle of 90 degree. It must make an angle of 90 degree. Now, some special cases, let us see. Here the cases will arise because of this angle theta. The case 1, when theta is equal to 0 degree, the angle between ideal and R, if it is 0 degree, that means dB you have chosen it on the wire. On the wire. This was your wire. Your ideal is going like this. And this was your angle theta. This angle theta is 0 degree, means this dB is chosen here. If you choose dB here along the direction of the current element, then all of you know that sine 0 degree is equal to 0. So dB will have minimum value. dB will become 0. This whole thing will become 0. It will give us minimum value. But in the second case, when theta is equal to 90 degree, if theta, here dB I am taking at this point, suppose dB like this, it is making an angle of 90 degree, then at 90 degree it will have maximum value. dB will be sine 90 degree is equal to 1, so it will be mu naught by 4 pi ideal divided by R square. You will get a maximum value. And if you try to take dB at an angle of 180 degree, you don't want to take here, you don't want to take here, suppose along this line. Here I am taking this time dB. Then the angle here between ideal and R, this is your R now, it will become 180 degree. So in that case also you will get 0. Minimum value of magnetic field you will get it. When theta is equal to 180 degree, the value of dB, here also sine 180 degree is equal to 0, so everything will become 0. You will get minimum value. So here what you should know is the value of ideal, the angle between ideal and the position vector. Position vector means it will tell us where the magnetic field you are going to find out. That line, it must not be along the direction of ideal. If it is on the top, angle will become 0. If it is at the bottom, angle will become 0. Along ideal, if you take, it will be always 0. You will not get any result. But if you take at 90 degree, you will get maximum value. If you take here, yes, you will get some value, but it will not be the maximum. If you take here, then also you will get value, it will get reduced. If you take here, it will get reduced, it will become 0 here. Like that dB, if you take here, you are getting maximum value. If you take here, it will become a little bit less, and here it will become 0. So these are the positions that you have to keep in mind while doing numericals. That part is essential. Along ideal, if you take dB, the angle will become 0 and there will be no magnetic field. There exists a relation between permittivity, that is your electrical permittivity, epsilon naught, and permeability, that is magnetic permeability, mu naught. Let us see the relation between them. If you multiply epsilon naught with mu naught, then if you multiply and divide by 4 pi epsilon naught, if I make it, and then with mu naught, if I divide 4 pi, then you can see here 4 pi epsilon naught, your value is 1 by 9 into 10 to the power 9, and mu naught by 4 pi, your value is 10 to the power minus 7. So this will give us 1 by 9 into 10 to the power minus 7, bring down, it will become plus 7, 9 plus 7 is 16. So you will get the relation like this, 9 into 10 to the power 16, so you can make it square, and it will be 3 into 10 to the power 8 square. And this is the speed of light in vacuum. We write it as 1 by c square. Or you can say that epsilon naught is equal to 1 by mu naught, if you bring down, mu naught c square. So this is a relation between these two, epsilon naught and mu naught. Now let us see some applications of Biot-Savart's law. The first application that we'll study is magnetic field on the axis of a circular loop carrying current. To find out the magnetic field on the axis of a circular loop, we'll take a circular loop like this, perpendicular, the plane of the loop will take perpendicular to the plane of the paper. We are keeping the loop like this. Suppose this is your loop. With center say C. You imagine this part is towards you and this part is behind, and allow current I to flow through it. Let us take the radius of the loop as A. Radius of the loop as A. This is your axis. Along the axis, at some point, suppose say at point P, I want to find out the magnetic field at a distance r from the center of the loop. Then in circle, you all know that if this is the center, just opposite to each other. Suppose a point A I have chosen here, there is another point exactly opposite on the other side of the center, or other side of the circle, B. If I take any point, suppose M, then just opposite to that one point you have here, N. So like that, all the points that are present in the circle, there are pair of points which are exactly opposite to each other. So that advantage we take here while finding out the magnetic field around the circular loop. What we do here, at the top end we choose the elemental length of the wire dl. In this case, if the current is going this way, it is coming like this it is coming, the direction of ideal will be towards you. It will come this way, it will come this way. ideal. In the board you can see that it's going this side, but it's not this side, it is towards you. And down part exactly opposite to that, if you take another elemental light, then here it will be pointing inward towards the board, and this is out of the board, or it is out of the paper. Here the direction will be inside the inwards towards the paper, like this. As you know that when an object revolves in a circular path, if you know the direction of velocity, then it's always tangential like this. In class 11 you studied the circular path. So here also that way you take it. This point let us mark it as L, suppose, and this point let us mark it as M. Just opposite to each other I have taken. I cannot draw this inward, so I'm keeping like this here. But you should know that one is coming towards you and the other one is going this side towards the board. Now, to find out the magnetic field at point P, this distance you have to know to apply Barth-Savart's law. This distance you have to find out. I'll write down some few lines here. Consider a circular loop of radius A and center C. Let I be the current flowing in the loop. Then P is at a distance R from the center C, where the magnetic field is to be determined. At this point P, we are going to find out the magnetic field. Now consider the current elements or current element ideal at 2 points L and M exactly opposite to each other, such that the current I at L is normally coming out of the paper. The circle is like this. At L, it is coming out of the paper normally at point L, and downside it is going normally inwards, such that the current is coming out normally to the paper at point or at L, and going inward normally to the paper. at point M. The outside one is going normally inward at point M. After doing this, after selecting 2 points L and M, then we'll use Biot-Savart's law. Now to use this angle is 90 degree. It is coming out of the paper normally, and there is one line like this, you can see, from L to P. So it is intersecting at an angle of 90 degree. Here the angle is 90 degree. This angle is 90 degree. So this distance we have to find out first. So in right triangle, LCP, this angle, Pythagoras theorem if you use, you can find out LP. LP will be square root of a square plus r square. A square plus r square. So LP will be square root of L square plus, A square plus R square. The same way, here also if you join one point, the line from M to P, here also you get the same thing, A square plus R square. Now you can use Biot-Savart's law at point P to find out the magnetic field. Let us use so dB at P due to the current element at point L. Magnetic field at P due to ideal at L is dB is equal to mu naught divided by 4 pi IDL sine theta is here 90 degree between this distance and this ideal, it is 90 degree divided by distance square. This is your distance square. If you do square, it will vanish. It will be a square plus r square. This will be the value of dB. Now, in this case, this sin theta is equal to 1. So, mu naught divided by 4 pi IDL divided by a square plus r square. Let us keep putting the bracket this one. Now, what is the direction of dB? Then you have to mention it. At this point, we found out dB. As we said that ideal and this r, we will take it as distance. This one r is coming. Your formula says ideal cross r. Is it clockwise or anti-clockwise? You have to check it. If it is, this is showing anti-clockwise like this. If it is anti-clockwise, the bottle cap, anti-clockwise, if you do, the bottle cap comes up. So the direction will be upwards, perpendicular to both of them, this distance as well as ideal. So it is in the upward direction. So along dB, the direction will be perpendicular upwards. This angle will be 90 degree. This angle here you can see it is exactly, it must be 90 degree. Likewise, magnetic field at point P due to the current element ideal at point M, you can find out, you will get the same magnitude. This magnitude will remain the same because here also ideal going inward and this distance will be perpendicular. One line going inside and then this line you are taking like this. One line you are taking from down like this. Here the angle will be exactly 90 degree between them. The magnitude will remain the same. the direction will change. Let me write down here, magnetic field at P due to ideal, and put arrowhead here indicating vector, due to ideal at point M. This is point M is, it will remain the same. dB is equal to mu naught divided by 4 pi ideal divided by s square plus r square. Perpendicularly, how it will be? This is ideal going inside. This is your distance r, or your distance here is not r, it's root over s square plus r square. Like this. It's like this. Going inside, and this is coming in towards me this side. Angle is 90 degree, but that is not important here. Your formula Balzer's law, it says ideal cross r, coming from here to here. Coming, if I do like this, coming from here to here, coming like this means it is going clockwise, like this. This is going clockwise. So if it goes clockwise, your bottle cap, if you rotate clockwise, it goes down. So it will be perpendicularly going downwards, like this it will appear. And it will be perpendicular to this distance. Here it will be 90 degree. So the direction will be normally or perpendicularly downwards. Perpendicularly or perpendicular downwards. So magnitudes are same. You can see very clearly, but the directions are different. Now, we need to resolve these two vectors dB into their rectangular components. Now, to resolve it, you check this triangle. You can see here this triangle, and if I draw this radius here, I'll get another triangle. These two angles are exactly equal. From the top of the circle, from the bottom of the circle, if you draw the lines, these lengths are equal, radius are equal. This is the common side, so the triangles are congruent, so the corresponding parts also must be equal. So let us take it as theta each. Now we'll resolve it. Resolving this dB into their components, if you say one line will take along x-axis, one line will take along y-axis. So this is 90 degree. Again, here you can see this is perpendicular. From here to here it is perpendicular. This is a horizontal line, this is vertical line. So this angle will be 90 minus theta. Now if this is 90 minus theta, so 90 degree minus this one, 90 degree minus 90 minus theta will give you this angle. 90 degree minus 90 minus theta will give you 90 minus 90 minus 2 minus this plus theta. So ultimately you will get theta. So this angle will be theta. So this angle, it is theta. Like that, downwards also, if you resolve it, you will get one along x-axis, one value you will get along y-axis, perpendicular component, horizontal component, and this angle will be theta. Now if this angle is theta, when you resolve, this angle is theta, when you resolve towards the angle, this vector is dB, so it will be dB cos theta. Base is there, so it will be cos theta. And this one will be dB sin theta. dB sin theta. Like that, here also, this is dB, the vector, and this one will become your cos, dB cos theta. and this will become your dB sin theta. Like this you resolve it. But we all know that the component dB, the magnitudes are same. These magnitudes are same. And cos theta, if you say in the triangle, it is base by hypotenuse. So r by root over s square plus r square, that value also will be same in both the cases. So these two components which are pointing in the opposite direction from the same point cancels each other's effect. They cancel each other's effect. Only the component which remains is dB sin theta. So write like this, resolving dB into their components, dB cos theta cancels each other's effect. Therefore, the net magnetic field will be given by only dB sin theta. Now here you have to be very careful. We are not taking all the points on the circle. We have taken only 2 points. Like that, many are there in a circle. So all the points will give dB sin theta, dB sin theta, dB sin theta, dB sin theta. Many of them will be there. So now, when you find out the net magnetic field, the net magnetic field, we'll write this integration, we'll have to do dB integration will give us B. I'm writing B net here, or simply B you can write down. It is the integration along the closed path. This is a circle or circular coil, so it will be a closed path dB sin theta. If only 2 vectors, then these two you would have added dB sin theta plus dB sin theta. Don't do this mistake. Many points are there, all are dB sin theta, dB sin theta, dB sin theta, dB sin theta. So one time only you take dB sin theta. But you are adding up that you are showing with this integration around the closed path. Now this one you calculate it. What is dB? You have found out already. That value you write down here. Mu naught divided by 4 pi I dl divided by s square plus r square, and this is sin theta. What is sin theta? Take this right triangle and find out. Sin theta is equal to perpendicular by hypotenuse. So it is a divided by root over s square plus r square. Now all the common terms you take it out. Integration you are going to do only for this dl. The remaining ones all you can take it out. This is mu naught divided by 4 pi, the magnetic constant. Then here you have IA divided by a square plus r square, and root over a square plus r square, it will be a square plus r square to the power 3 by 2. Here power is 1 and here power is root over means half. 1 plus half is equal to 3 by 2. The power will be 3 by 2. And integration around the closed path dl, that you are going to do integration. So here you have mu naught IA divided by 4 pi s square plus r square to the power 3 by 2 into integration of dl. dl means a small portion of the wire. Whole integration will be the circumference of the wire. And circumference formula, you know, it is 2 pi the radius r, 2 pi r. But here radius is not r, r is the distance, radius is a. So you write 2 pi a. There will be 2 pi a. Now pi you can cancel out. 2 times is 4, and this a into a will become A square. So I write down the resultant magnetic field B at point P is A into A is A square. So it is mu naught I A square divided by 2 times A square plus R square to the power 3 by 2. So this is your resultant magnetic field at point P. This is the circular loop. And what is the direction? Then you can see very clearly that this direction only it will go, because all you added up, all dB centimeter is going like this. It is along the axis away from the center. The point P you have chosen along the axis of the circular coil. Along the axis away from the center. See, like this you can give the direction. This is the magnitude and this is the direction. Let us see the other case, the second case. Magnetic field on the at the center of the circular loop carrying current. At the center of the circular loop, center of circular loop carrying current. Then in that case, what will be your expression? Now if this center is brought, the point P is brought at the center, this value of R will be 0. The value of R will be 0. So if value of R is equal to 0, from here you can find out this A square to the power 3 by 2 will become A cube. Then A square and A will cancel, you will get the expression for magnetic field at the center of the circular loop carrying current. So at the center you can find B is equal to, you can take the same expression, mu naught I A square divided by 2 times A square plus R square to the power 3 by 2. When R is equal to 0, B is equal to mu naught I A square divided by 2 into, this is 0, so A power 2 multiplied by 3 by 2, this 2 will get cancelled. You will get mu naught I A square divided by 2A cube. A square and A cube, if you cancel it, 1A will remain. So it will be mu naught I divided by 2 times A. So this is the expression for magnetic field at the center of the coil. Now here A indicates radius, remember, A indicates radius. You can write R also, you can write A also, depending upon what type of circle you have drawn. If you take the radius as R, you write R here. If you take it as X, you write here X. But you should know that I is current and A is the radius of the coil. Suppose here is written A, so that's why it's written here A. Now here also, if magnetic field is found out at the center, then you will be interested to know the direction, how to find out the direction. In this case, we know we took the current in the anti-clockwise direction. That's why the direction of magnetic field is going away from the center. If the direction of current will come in the reverse order, that is in the clockwise direction, then the direction of magnetic field will be inwards. It will come like this, towards the center of the coil. These points are to be noted. Now, let us check here how to find out the direction. Here you can use your Maxwell's right-hand grip rule again. Earlier we took, if thumb shows the direction of current, then the tips of the finger encircling the conductor shows the magnetic field lines. But in this case, current is in the circular direction. So this will become current and this will become magnetic field line. I think you got it. Change it. This one make it field line. Sorry, this one make it electric current, and then this one you can make it as the direction of field lines. So if the current is in anti-clockwise direction, upward direction. So in this case, if current is in anti-clockwise direction, the direction of magnetic field lines will be coming perpendicularly towards you. It will be coming perpendicularly towards the paper, perpendicular to the plane of the paper. If it is in clockwise direction, it will be inwards, perpendicularly inwards. It will go inside the plane of paper. So when current is in the direction will be, yes, we are taking an anti-clockwise direction. The direction it will be along the plane of the paper and perpendicular outwards, perpendicular outwards to the plane of the paper. So use this one, anti-clockwise. Current is in anti-clockwise direction. It should be perpendicularly outward. If you do like this, you will check it here. Clockwise, then it will go inwards. If you look from there, do like this, anti-clockwise direction of current, perpendicularly outwards. The reverse will be, if it is clockwise, then it will be perpendicularly inwards. That you have to know it clearly. Let me draw one diagram to show the direction of magnetic field line. Suppose I am taking the loop like this. This part is this side towards the board, and this part is facing towards you, suppose. This is your circular loop. If the current is going, let us say clockwise this time, current is I. You think like this, it is kept this way, the circular loop, like this it is kept. This part is towards you, and this part is the other end, like this it is kept. Then current is going in the clockwise direction. Then the field line should go downwards. This one again do. Your right hand rule, thumb rule you can use. Anti-clockwise, upside. Then clockwise will be downside. Clockwise if you do, the reverse is also true. Clockwise if you do, will be downside. The downside, then at this point, suppose this is the center, you get a central line like this. It's going downward. Arrowhead will put downside. And then this side, curve, you will put it. This side also, curve it. And at this point, we will put circle like this. At this point also, we will put circle like this. All pointing downward, then downside. Here downside, then it will become anti-clockwise. And here downside, then it will become downside. Like this only you will put it, then it will become clockwise. One side will be clockwise, one side will be anti-clockwise. You may think that why these lines are curved, but we know from magnetism that if this is north and this is south pole, then the magnetic field line starts from the north and it goes towards the south, outside the field, but inside the field it goes from south to north. Magnetic field lines are closed curves. That's why when we are taking the ring like this, field lines are inside, from inside, outside is coming in circular pattern like this. If I take the curve like this, field lines are going like this, circulating the wire. It is circulating the wire. The half part we are not drawing. If you look very carefully, these lines are not, if this is the curve, this arm is the curve, the lines are going like this it is circulating. So we are drawing only one part, like this curve only we are drawing. remaining part we are not drawing. So you should know that it is like this. It's not intersecting the wire. It is not intersecting the wire. From here the curves are formed, like this will be formed. Here like this will be formed. That's why at this end we took circle like this, round. At this end also we took circle like this, round. So like this you have to draw. And then if the current direction is in anti-clockwise, then also you draw the same type of pattern, but you point upwards, like this, like this, like this, like this, upwards you have to point, like this. And at these 2 points, we will draw circular like this. And follow this arrowhead up, so this will be clockwise. If follow up, then it will become anti-clockwise. Like this, you have to draw the field lines for a circular current carrying conductor. Now you will be interested to know if this circular ring, it has magnetic field, then surely polarity should exist, one north pole and one south pole. Now how to find out the polarity of the wire, which side is north and which side is south? This rule we call it as clock rule. Clock rule. It's simple as it is. It's very simple. You draw 2 circles like this, one right north and one right south. S, north and south. S, it should look like S and it should look like north. North means like this, current is coming anti-clockwise. Here current is going clockwise. So this one will tell you. If the wire which is facing, suppose I am keeping the wire in my hand like this. If the current is coming in the clockwise direction, if it is coming in the clockwise direction, then you will follow this one. Clockwise direction, current is flowing. It is going the clockwise direction like this. Then the wire which is facing towards me will be south. The wire which will face towards us will be south. And if the current is in the anti-clockwise direction, the wire which is facing towards you will be north. This end will tell you. Suppose this is the wire. This is the wire. Current is going like this. Suppose wire is in this shape. Current is going like this. That means it is going in the clockwise direction. Correct? Like this going. No, it is anti-clockwise direction. Anti-clockwise direction. And if it is anti-clockwise direction, the wire which is facing towards me means this part of the wire will be north and this part will be south, and vice versa. If it is in clockwise direction, this part of the wire will be south and this part will be north. That is how you can find out with the help of clock rule. Let us do one numerical and see using Biot-Savart's law. 2 very small identical loops, 1 and 2. 1 and 2. They are identical, so their radius, we'll take it as AH. This is loop 1 and this is loop 2. Carrying current I are placed vertically with their geometrical axes perpendicular to each other. These are the geometrical axes. They are perpendicular to each other at point O. You are asked to find the magnitude and direction of the net magnetic field produced at point O. Here the net magnetic field to find out. So here to use Biot-Savart's law, this loop you can see the current is passing in the clockwise direction. While deriving, it derived in the anti-clockwise direction. Anti-clockwise direction, the field is to go this side, away from the center. But if it is clockwise, it will come towards the center. This side will appear V1. So using Biot-Savart's law, let us write down the magnitude of V1. So solution, when you do magnetic field at O due to coil 1 is, let us write it as V1. V1 is equal to mu naught I A square divided by 2 times A square plus x square to the power 3 by 2. This is your formula. towards the center of the coil. Direction is towards the center of the coil. Then the next one, that is for the second loop, you can see that the direction of current is in the clockwise direction. Sorry, it is in the anti-clockwise direction. So it will go away from the center, look like this. Direction of V2, this is for the second coil, will be in the upward direction. It will be in upward direction. So right here, magnetic field at O due to coil 2. Coil number 2 is, we'll write it as B2. Here also formula will remain the same because distance are equal, x, radius also equal a. So radius square divided by 2s square plus x square to the power 3 by 2. Only the direction will be different, away from the center of the coil. Now the net magnetic field, you will get it along the diagonal. These two are co-initial vectors. These are like the two adjacent sides of a parallelogram. So if you find the net magnetic field, this will give you the net magnetic field B. The net magnetic field you can find like this. The net magnetic field at O due to the coils, the two coils, will be or is B is equal to square root of B1 square plus B2 square plus 2 times B1 B2 cos theta. But here theta, the angle between the two vectors is 90 degree. This is 90, so this is also 90. So cos 90 degree is equal to 0. So we don't write the third term. So this will give you the net magnetic field. So B will be square root of B1 and B2, their magnitudes are same. Mu naught I a square divided by 2 times a square plus x square to the power 3 by 2 whole square plus mu naught I a square divided by 2 times a square plus x square to the power 3 by 2 the whole square. Like this you'll get it. Now this one, square root of, both the terms are same, both are under square, so we can write 2 times mu naught I a square divided by 2 a square plus x square to the power 3 by 2 whole square. Like this will appear. Then this square term, you can take it out of the root. That is mu naught I a square divided by 2 a square plus x square to the power 3 by 2. Square and root will get cancelled, but this 2 is under the root. So here one root 2 term will come. So this will give you the magnitude. And to find out the direction, you can mark an angle here, theta say, along x-axis. If you mark the angle theta, tan theta is equal to perpendicular by base. Perpendicular is B2. This one is B2. This is B1. So it will be B2 by B1. To find the direction, tan theta is equal to B2 by B1. B2 and B1, the magnitudes, you know that both are equal. So it will give us 1. So tan theta is equal to 1. Theta is equal to tan inverse of 1 is equal to 45 degree. This will give you the direction. Or you can write here therefore direction theta is equal to 45 degree. This way you can find out the magnitude and direction using Biot-Savart's law. One very important thing I want to tell you is for a circular coil, whenever you find out the magnetic field, you got mu naught divided by 4 pi, mu naught divided by 4 pi magnetic field B. You are getting the expression like this: mu naught I a square by 2 times a square plus x square, or sometimes r square. Distance, if it is r, it will be r square. This is the expression. But this is for a single ring. If you have more than one ring, 2 rings, 3 rings, 50 rings, 60 rings, then number of turns also will come. This is for one turn. For n turns, then it will come n times mu naught I a square divided by 2 times a square plus x square. Like this will appear the expression. Power is 3 by 2. So whenever you are doing coil, while solving, you are solving for one coil. If more coils are there, then how many coils are there? That many times you have to multiply. Not only to find along its axis. When you find out the magnetic field at the center of the coil, also the same thing. For a single coil, what you get the answer or the solution. For 2 coil, it will be 2 into. For 3 coil, it will be 3 into. So the number of coils, if it is there, then you multiply with the number of turns of the coil, that is n. Thank you and have a nice day. Stay tuned with LFI Educates.